Hello and welcome to lesson 1 of week 4. In this lesson, we are going to look at the Radix sort algorithm. My name is Mildred. The Radix sort algorithm is a non-comparative sorting algorithm that sorts numbers by processing their digits, one digit at a time. And how it does this is it either starts from the least significant digit or the most significant digit. And when we say least significant digits, we're talking about processing digits from right to left and most significant from left to right. Okay, and so what it does is that it looks at the different place values of the numbers in an item. So we have the units place, the tens place, and the 100 place, the 1000 place, like that. So if we have, for instance, an array that has let's put some numbers here, 170, 90. So we have this array, and let's say we want to implement this using Radix sort. We first of all look at the numbers we have. We have the units place, we have the tens, we have the 100 place, and the maximum number of digits we have is 3. So if this were to run manually, the first run will give us, we are looking at the units place first. So we'll look at everything that has zeros in the units place. And because we're using a stable sorting algorithm, when we sort, we want to leave it relatively in the position that they occur. So we'll say 170 first because it has 0 in the units place. And then this one has 5, 90 has 0 in the units place. The next one we'll have is 90. Then we have 2 next. So we go here back to the beginning and we see 802 is the next one. And then we have 2 there. And then after 2 we have 24. And then we look to see we have 45. And then we have 75. And then we have 66. So that's the first run. The second run is going to now become, we are looking at the tens place now. Now the tens place is to look at this second number here. We don't have a tens place for some of these, but how it works is that we'll look for the smallest one first. So in the tens place, 802 has 0 in the tens place, and so the next smallest in the tens place is the number 2. Then the next is the number 24. Then the next is the number 45. Then the next is the number 66. Then the next is the number 75. And then so it will be 170 before 75 because you want to make it in relative position. It comes before 75. So if they are the same, you want to keep them in relative position. And then we have 90 as the last one. Now this is not sorted yet. Then let's do the third one. Now we're looking at the 100 place. In the 100 place, we're going to start with 2, 24 because they don't have the 100 place, 45, 66, 75, 90, and now we want to look at the ones that has in the 100 place, 170 and then 802. And now you see that this is already completely sorted by the time we do that. Okay, so this is what we want to implement. We want to say we will implement the counting sort because we need to use a stable sorting algorithm to implement the Radix sort. So we'll start with the counting sort. For this time, we're going to have an exponent when we create the counting sort. So I'm going to do it like this. The counting sort, we'll have the array and we want to give the exponent. Okay, now we want to get the length of the array and we want to create 2 arrays or 2 lists. One will hold the output and we'll just let 0 fill this. We'll say 0 and we'll fill this with zeros to the length of the array. And then we want to have the count. This is going to have the count array that will hold the digits from 0 to 9. So we are counting 0 to 9. Those are all the digits we have. So 0 times 10 because 1 0 1 2 3 4 5 6 7 8 9. That's what we're going to store. So we have these 2 arrays with this. We want to store. So this, for this count, what we are going to store here is the occurrence that will come here, just like we did in the counting sort. But we have 0 to 9, so that's what we'll have. And then we want to now loop through items. And when we loop through, we want to get the digits at the current place value, right? So let's get the index. Let's call it index is equal to the. So let's do a loop first. So we'll say for I in range n, we want to get an index is equal to array. So we'll say array I, and we'll use the floor to divide this by the exponent, and then we use modulo 10. And we're using modulo 10 to extract the last digit of the number after dividing by this exponent. And this exponent we say is just expressing or just representing the current digit place. So we say 1 for units, 10 for tens, 100 for hundreds, and like that. When we do this, we'll just increment the count. So we'll say count index plus equal 1. Now when we've done this, we want to change the count so that it contains the actual position of this digit in the output, right? So let's loop through that. For I in range 1 10, okay, so we want it to start from 1 and stop at at 10, but 10 is exclusive, so it will be 1 to 9 that we'll have there. So for I in range 1 to 10, we'll say count I plus 4 count I minus 1. So we want to build the output array, and what we want to do is to traverse through the input array in reverse. When we traverse through, what do? We say for I in range, so we're doing it in reverse. So we're starting from the n minus 1, right? We want to get the last index position, so we're starting from the last index position n minus 1, and we want to go from there to the beginning because we're counting from behind. So minus 1 will get us to the beginning, and then we want to go backwards. So we want to increment, because the range only increments by 1 positive, but we want to make sure the step is minus 1, so it goes negative, all right, like that. So we traverse the input arrays in reverse like that. All right, I want to find the digits at the current place value. Now we'll say the index is equal to array I and the exponent divided by exponent modulo 10. All right, and then we'll place the element in the output array at the correct position. And so for that output array, we want to get the correct position, so we'll say count index, right? I think it's like this, and minus 1 is equal to the array at the ith index. We'll decrease the count for this digit, so we'll say count index, so we'll say minus equal 1. Now we want to copy the output array so that the array now contains the sorted numbers. So we'll say for I in range n, we want to say array I is equal to output I. Okay, so I think this is how we implement the counting sort to be able to use for the Radix sort. So now let's say def Radix sort. So the implementation will now be straightforward, and here we'll pass in the array. We want to say if the length of the array is equal to 0, we want to return just the array. There's nothing to sort. But if not, we want to get the maximum number so that we know the number of digits it has. So we'll know whether we have ones, tens, hundreds place, right? So let's get the max num is equal to max array. All right, and then we want to do counting sort for every of the digits. So our exponent is equal to 1, and we'll do counting sort for everything. So we'll say while max num divided by, so we use the floor operator, the exponent is greater than 0, we want to now use counting sort that we implemented above here, and we'll pass in the array and our exponent, which is 1. Then we will say the exponent times, so exponent will be equal to exponent times 10, so we'll say exponent times equal 10, like that. And then now we can return the array. So if we try this array to sort this array now, let's see whether this Radix sort sorts this array. So when we say if name equal to main, we want to say simple array is equal to this, and then let's say print original array, so we'll do this as simple array, and then we want to sorted array is equal to Radix sort, and we'll pass in the simple array, and then we'll print sorted array, and then when I run this, we have this sorted completely. So we see that this works. So you want to replay the video over and over again, refer to your lesson resource, and think about other ways you can do this using the counting sort. You can also use other sorting algorithm, but you need to use a stable sorting algorithm so that you can achieve this easier, and then you use that stable algorithm within your Radix sort algorithm here. All right, so looking at this, we can now talk about the time complexity. It will depend on both the values that need to be sorted and the number of digits in the highest value. Then the space complexity will be like it would be like n plus k because of the extra space for counting that we need. And then the worst case for this would just be like if there are many digits in the highest value as there are values to sort. Let's say the highest value contains 6 digits, 7 or 8 digits, and the number of values to sort is like millions of values to sort. This will be the worst case, which would now end up being n squared. And the best case will not be that way, where maybe you have 1 million digits or a billion digits, and the highest digit is just 3 digits, maybe 999 or something like that. Way you may get this in the best case. And so since the worst case gives you n squared, you want to still explore more sorting algorithm that can have the best worst case scenario. This is best when you want to sort integers or strings of fixed length, or you want to use this for a large data set where the number of digits is small, but it's not good for large keys with many digits at all. So this is where we end this lesson. In the next lesson, we are going to look at another sorting algorithm called the merge sort. Thank you, and see you in the next lesson.